Welcome to qnawire.
In this problem, we're going to talk about the relativistic energy. And what we need to remember is that the relativistic energy is equal to the total energy of a particle is equal to gamma mc squared. Okay, and this is equal to the rest energy of the particle, which is mc squared, plus the kinetic energy of that particle. Meaning that we can write the kinetic energy as gamma minus 1 times mc squared. And we need to remember that gamma is 1 over the square root of 1 minus v squared over c squared. Besides, we also need to remind ourselves of the relativistic transformation of velocities. Transformations of velocities. So consider that we have a reference frame. Okay. And in this reference frame, we have two particles. The first one, this red one here, is moving with a speed v. The second one, this green one, is moving with a speed capital V. Okay. I'm going to call this reference frame the S reference frame. Now consider that we have a second reference frame in which the first particle is at rest. Okay, so the red particle has no velocity according to this reference frame. And we ask ourselves, what is the velocity of the green particle v prime? According to special relativity, v prime is equal to capital V plus v divided by 1 plus capital V over c squared. And now we can move on to our exercise. So we have a reaction, collision actually, a proton-proton collision that results in the following. We have two protons. One of the protons is at rest, the other one is moving. They collide and they generate two protons plus two kns, one positive and one negative kn. And we need to remember that the mass of the proton is 938.3 megaelectron volts, while the mass of the kn is 493.7 megaelectron volts, of course, per c squared. Okay, so what we need to find in question A is what is the minimum kinetic energy of the moving proton. Remember that one of them is moving, the other one is at rest. We need to find what is the minimum kinetic energy of the moving proton such that this reaction can occur. Notice that there are two conservation laws that we have to apply here. The first one is the conservation of energy, so the initial energy must be equal to the final energy, and the conservation of momentum. If we work in a reference frame where the initial momentum is non-zero, such as the lab reference frame where the two particles, when one of the particles is at rest, the other one is not at rest, so pi is different from 0, in this reference frame, things are going to get very complicated very soon. So we're not going to work in this reference frame. Instead, we're going to move on to the center of mass reference frame. And then from that reference frame, we can go back to the lab reference frame afterwards. But all the initial calculations we're going to do in the center of mass reference frame. In this reference frame, the total momentum of the particles is 0, the total initial momentum. So the final initial momentum is also going to be 0. This makes the second equation, the conservation momentum, trivial and makes things a lot easier. So notice that in the lab reference frame, we have a proton moving, another one at rest. The proton that is moving has a certain kinetic energy and a certain velocity v. The second one has neither. But in the center of mass reference frame, both protons are moving with the same speed. Since they have the same mass, the total momentum is zero, then they must have the same speed, just at opposite directions. And I'm going to call these speeds u. Okay, they're not going to be the same as v, because v is the velocity in the lab reference frame, and u in the center of mass reference frame. Of course, they are connected. These two velocities are connected by the fact that v is equal to the sum of the velocities, the two velocities in the center of mass reference frame, divided by 1 plus u squared over c squared. Okay, this comes from this equation here that I talked about when I was talking about transformation of velocities. So let's keep this equation in mind. We're going to need this equation after we work in the center of mass reference frame. Okay, so in the center of mass, everything is a lot easier because the initial energy is the kinetic energy, 2 times the kinetic energy of each proton, plus the mass, the rest energy of the protons, that's 2mPc squared, that is equal to, and we want to know what is the minimum kinetic energy. This means that we want the final state with the minimum kinetic energy as possible. In the reference frame where the initial momentum is zero, the minimum kinetic energy is allowed to be zero. And this is what makes this calculation so much simpler. Okay, the final momentum in this reference frame is zero. So the final kinetic energy in this reference frame is zero. So this is 2 times the rest energy of one proton plus 2 times the rest energy of one kn. The protons rest energy cancel out, so the kinetic energy of one proton must be equal to the rest energy of one kn. And the rest energy of the kn is the mass times c squared. That's 493.7 megaelectron volts. Okay. And now with this information, we can calculate gamma. So remember that K is gamma minus 1 times mc, P, this is the mass of the proton, C squared. This is the mass of the Kn, C squared. The C's cancel out, and gamma is 1 plus the mass of the Kn over the mass of the proton. This is 1 plus 493.7 divided by 938.3. So gamma is equal to 1.526. Okay. With this, my goal is to calculate what u is. That is, what is the speed in the center of mass reference frame, the speed of each particle. And with this, we can calculate the speed of the incoming particle in the lab reference frame where the other particle is at rest. Okay. So remember that gamma is 1 over the square root of 1 minus v squared over c squared. And from this, we can obtain that v is the square root of 1 minus 1 over gamma squared times c squared. So v is the square root of 1 minus 1 over 1.526 squared c. There's no squared here, sorry for that. So v is equal to 0.755 times the speed of light, c. Okay, this is actually, I shouldn't have called this v. V was the name I was giving to the lab velocity. This should be u. This is the center of mass velocity. Just for me to be consistent. So this is U, and our goal is to find V now. With V, we can calculate what is the kinetic energy of the incoming particle. Now, remember that I told you that V, up here, V is equal to 2U divided by 1 plus U squared over C squared. So this is 2 times 0.755C divided by 1 plus 0.755 squared. So V is equal to 0.962 times the speed of light. Okay. Now we're in a position to calculate the kinetic energy. That's gamma minus 1 times the mass of the proton, C squared. Gamma minus 1 is 1 over the square root of 1 minus V squared over C squared. Minus 1, times M, the mass of the proton, that is 938.3 megaelectron volts per C squared, then multiplied by C squared, and the C squared is cancelled out. So K is equal to 2,498 megaelectron volts. And this is the answer to question A. In question B, we have to calculate how much greater this is than the combined mass of the two kns. So the combined rest energy, of the two kns. So we have to calculate K divided by 2mkc squared. So this is 2,498 megaelectron volts divided by 2 times 493.7 megaelectron volts, and this is equal to 2.53. So the kinetic energy is 2.53 times greater than the rest energy of the kns. Okay, and in question C, we have to assume now that in the lab reference frame, the two protons are approaching each other with the same speed but at opposite directions. Okay, just as in the center of mass reference frame. The difference is that now the center of mass reference frame and the lab reference frame are the same ones. And our goal is to calculate in this reference frame how much kinetic energy is needed in order to create these kns. So basically, this has already been calculated because, as I told you before, this is exactly the same as the center of mass calculation we carried out. And the kinetic energy we found for each proton is that the kinetic energy is 493.7 megaelectron volts. It's right here. So the kinetic energy for the two protons, the total kinetic energy is 2 times the kinetic energy of a single proton. So that's 2 times 493.7 megaelectron volts. This is 987.4 megaelectron volts. Now this is exactly 1 time the mass of the two kns. We get a combined mass of the two kns. And this concludes our exercise.